So in this lesson we're going to have a look at some standard integrals and some standard trigonometric integrals as well. So we'll get started straight away. So the first type of integral that I want to have a look at are integrals of the form the integral of f of ax plus b dx. And these are a standard type of integral that you'd be expected just to reel off. So all of these integrals that I'm doing, by the way, or most of the integrals that I'm going to do today rather, are going to be substitution integrals, but where the result is so standard, where the process is so mechanical, that you're able to basically just jump past the working out and go straight to the answer. And the exam board expect you to do that as well. The number of marks in a question are reduced as a result of the results being standard. So let's take an example. Let's take, for example, the integral, get the right pen drawing tool there, the integral of, and let's say 3x plus 12 to the power of 12 dx. So what we're going to do with this one, we're going to do it by substitution first of all and show you why that this is an integral by substitution, but just missing out the working. So what I'm going to do is let u equal the bit in the bracket 3x plus 12, which means that du by dx is equal to just 3. Rearranging that a bit, that implies that du equals 3 dx, which means that dx is a third du. So we're ready to piece this back together now. So that becomes the integral of, well, in the bracket is u to the power of 12, and instead of dx, we're going to write a third du equals, so the integral of a third u to the 12 du equals, so that becomes a third u to the 13 over 13 plus c equals 1 over 39 3x plus 12 to the 13 plus c. So that's doing it the full integration by substitution method. However, what we're allowed to do, and this only works when the thing in the bracket is linear, when it's a linear function wrapped in another function, we can skip out all of this middle part here and just go straight in for the answer. So again, I'll emphasize this only works when we've got a linear function wrapped in something else. And we can use the reverse chain rule here. So let's do this again, but how it will be expected to be done in an exam. So the integral of 3x plus 12 to the power of 12 dx. So I can see that I've got a linear function, 3x plus 12, wrapped in another function, wrapped in a power of 12. So that there is equal to, and what we're going to do, we're just going to use the reverse chain rule, add 1 to the power, divide by the power, but also an extra step, we're going to divide by the differential of what's in the bracket, so make the bottom 3 times bigger, plus c. And notice that's the equivalent of what we've done here. We've integrated the full thing to get u to the 13 over 13, and then we've multiplied here, multiplied the denominator by the differential of the bracket, or the equivalent divided by the differential of the bracket. And I have to emphasize, I can't emphasize strongly enough, this rule only works when we've got a linear function wrapped in another function. So that's equal to, summarizing, 3x plus 12 to the power of 13 over 39 plus c is that integral there. So let's try another example. And let's go about doing this the quick way now. So let's say we've got, for example, the integral of root of 5x plus 2 dx. Notice that this rule can be followed now because we've got a linear function, 5x plus 2, wrapped in another function, wrapped in a square root. But let's write that in a more integration friendly format. Equals the integral of 5x plus 2 to the power of a half dx. And let's go straight in there. Equals. So I'd want the power 5x plus 2 to the power of 3 over 2 divided by 3 over 2, divide by the new power, which is the same as timesing by 2/3. But also, remember this extra step, divide by the differential of the bracket, i.e. make the denominator, in this case 5 times bigger. The differential of 5x plus 2 is 5 plus c equals 2 lots of 5x plus 2 to the 3 over 2 over 15 plus c is the answer. And there's a whole host of other situations, other different functions that we can apply this to. Always though, linear functions wrapped in another function. So let's try it with this one here. So the integral of, let's say, e to the 6x minus 3 dx. So we'll see we've got a linear function, 6x minus 3, wrapped in another function, wrapped in the e function. So that becomes itself. Integrate e to the something, we get e to the something back. But remember, the extra step, divide by the differential of the bracket. And substitution will always do the job here. But as I say, it's a bit overkill to do the full substitution method. What we should do is just recognise the linear function wrapped in another function and reverse differentiate it. Use the reverse of the chain rule. So let's try another. So let's try the integral of, I don't know, let's say cos of 2x. And this is where it really becomes useful, ones like this, which are pretty standard exam questions. And doing a full substitution method, rather than just reeling off the answer, would be quite wasteful. So the integral of cos of 2x. So if we integrate cos, we get sine. But remember, the extra bit, divide by the differential of the bracket, divide by 2 plus c. So to do a full substitution method for that, when it probably is only going to be worth 1 or 2 marks, would be quite wasteful. Try one more before we move on to another type. Let's say the integral of 1 over 7x plus 3 dx. So remember, the integral of 1 over x is log mod x. So that's what we're going to do here. Log modulus of whatever's in the bracket. And again, the only reason this works is because what's in the bracket is linear. It's a linear function wrapped in another function, in this case wrapped in a power minus 1. Divide by the differential of the bracket, must remember that, plus c. So that's that type. So now what we're going to do is take a look at what the various different formula booklets across the different exam boards actually give you in this. So let's have a look at Edexcel, what they give you in terms of integration in their formula booklet. So there's integration, but also what you'd find useful is some of the differentiations as well. So some of the differentials rather. So I'll just pop those there. So notice in Edexcel, you're given all these different results, standard results for integrating and differentiating. So here we integrate sec squared of kx, we end up with that. We integrate tan of kx, we get that. Likewise, we're given differentiations as well. However, we can use this in reverse. We can then deduce that the integral of this particular expression here is that. The integral of that expression is that. So they're all quite useful. When it comes to OCR's formula booklet, we'll see that's a bit stingy in what it gives you. It doesn't even give you any of the trig integrals. So we're expected to be able to use these tables of differentials in order to derive the integrals. So we know that the integral of sec squared x is tan x. The integral of sec x tan x is sec x. The integral of minus cosec squared x is cot x. or we can derive from that the integral of cos x squared x is minus cot x, and likewise for this one here. So we're expected to be able just to use that in order to derive the different integrals. But an extremely important thing to do now is to have your formula booklet to hand whenever you're doing any integration questions, because some of them require you to use it. So get one printed off or have one electronically next to you while you're doing these questions, because it's so important. So let's do a few examples that use this. So let's leave that on screen. So let's say we've got the integral of cosec a quarter x cot a quarter x dx. So this one here is going to be the useful one. So we know that the integral of minus cosec x cot x is cosec x, but this is quarter x, so we'll replace the x with a quarter x. So this is another one of those linear functions with another function wrapped around it, a quarter x, and we've wrapped around it cosec cot. So the integral of cosec x cot x we can derive from this would be minus cosec x. So because it was a quarter x, going to do that. And remember, what we need to do here is divide by the differential of the bracket, divide by a quarter. So actually, that puts a 4 at the front. Plus c, so it's minus 4 cosec a quarter x. Let's try another one. So let's do the integral of cosec squared of 12x dx. So again, looking at our table of reverse differentials, and if you're an AQA or OCR, you're a bit more fortunate that they give you the integrals as well. But we're stuck with this for now. We'll use the OCR one. So the integral of cosec squared is minus cot. Of 12x plus c, but don't forget the extra bit. Divide by the differential of the bracket. Divide by 12. Let's try another. So how about this time the integral of 1 over cos squared of 8x minus 3 dx. Notice that doesn't directly appear in the table. We've got to rewrite this in a more integration friendly format. So 1 over cos is sec, so 1 over cos squared is sec squared. So that actually becomes sec squared 8x minus 3, the integral of dx equals, so the integral of sec squared is tan. You can see from the table there. But remember, divide by the differential of the bracket. Divide by 8 plus c. So again, linear functions wrapped in other functions are relatively straightforward to do. Let's try a different one though. Let's try the integral of tan x dx. And notice the integral of tan x isn't given in this table, but it is given in the Edexcel formula booklet. So if you're asked to just state the integral, just use the formula booklet. However, you might be asked to prove it, so let's do it as if you had to show full working. The integral of tan x dx. So let's write that as the integral of sin x over cos x dx. And what we're going to do this by means of a substitution. So we're going to let u equal the denominator cos x, which means that du by dx equals minus sin x. And that in turn means that dx equals minus 1 over sin x du. So we're ready to integrate now. So that's equal to the integral of sine x over u, because u was cos x, times minus 1 over sine x du, like that, which then simplifies to the integral of minus 1 over u, which is equal to log modulus of u plus c, and don't forget the minus sign at the front there, equals log modulus of and u was cos x, log modulus of cos x plus c, not forgetting the minus sign at the front, which isn't the result given in the Edexcel formula booklet. So what they've done in the Edexcel formula booklet, this minus sign at the front is actually minus 1. They've taken that, using logarithm laws, into the log as a power. So actually that becomes equals log of, and the, power minus 1 means reciprocal. The reciprocal of cos x is sec x plus c. So they've taken that minus 1. So that now says cos x to the power of minus 1, i.e. the reciprocal of cos x, which is sec x. So there's that result there. So we'll keep going. Let's do, again, the integral of cot x. So the integral of cot x dx, using a similar method. So the integral of cos x over sin x dx, which is equal to, so let's change that. Let's do a substitution, let u equal sin x, which means that du by dx equals cos x, which means that dx equals 1 over cos x du. So we can change that now to be cos x over u times 1 over cos x dx, giving just the integral of 1 over u du. Likewise here, I should have written du equals log modulus of u plus c, and the final answer log mod sin x plus c. So if you asked to derive that, that's how it would be expected to be done. So moving on to another type of integral now. There's a special method for these ones that you just need to learn. So lots of methods you need to know for integrating trig functions, but this one in particular. So we're going to go through the integral of cos squared x dx and the integral of sine squared x dx. And these, when you see these ones, have their own special method. So we'll start with the integral of cos squared x. Let's just have a go at it. So the integral of cos squared x equals, and the method that you need to learn in order to do this, when this happens, when you see the integral of cos squared x or the integral of sine squared x, we're going to expand cos 2x using double angle formulae. So what we're going to do, expand cos of 2x. So the issue is, as it stands, we can't integrate cos squared of x, but we can turn it into something. We can rewrite cos squared of x using trig identities in a different form that we can integrate. So taking the relevant expansion we want in terms of cos x, because cos squared x we're trying to integrate, and there's no substitute here for just learning your trig identities to cos squared x minus 1. You've just got to know that. So let's rearrange this to get cos of 2x plus 1 equals 2 cos squared x. Then divide by 2, we get a half cos of 2x plus a half equals cos squared x. So what we've done now, we've taken something that we can't integrate and turned it into something equivalent that we can integrate. So actually, let's go for it now. The integral of a half cos of 2x plus a half dx, which using the rules we've learned previously in this lesson, that becomes, well, cos integrates to sine, so that becomes a half sine of 2x. But remember, we must divide by the differential of the bracket, we must divide by 2. So that actually turns that into a quarter, plus a half x plus c, and that's that done. Let's do it for sine squared x as well. Let's integrate sine squared x using this newly found rule. So the integral of sine squared x dx, well again, let's expand the double angles. So cos of 2x equals, and we should just know the expansion of cos of 2x, it's 1 minus 2 sine squared x. So that means that 2 sine squared x equals 1 minus cos of 2x. Divide by 2, which means that sine squared x equals a half minus 1 half cos of 2x. So we've taken something we can't integrate, sine squared x, and we've turned it into something equivalent that we can integrate. So equals the integral of a half minus 1 half cos of 2x dx equals 1 half x minus, for the same reason as before, 1 quarter sine of 2x plus c. So that's how to integrate cos squared x and sine squared x. So now might be a good time to pause and have a look at some of the worksheet questions on this, but we'll plough on ahead anyway. So let's extend on this. Let's have a look at how to find the integral of cos squared of, let's say, 10x dx. So what we're going to do, we're going to use the same expansion that we did before. There it is there. So let's just copy and paste that down there, except notice this time the difference between this and the previous question is that x has been replaced with 10x. So if we do that on this identity here, if we replace x with 10x, and here that would make that 20x, replacing x with 10x. We've got another identity that we can use so that we can do the question. So now let's rearrange this to get cos of 20x plus 1 equals 2 cos squared of 10x. Dividing by 2, we get a half cos of 20x plus 1 half equals cos squared of 10x. So now we've taken something we can't integrate, cos squared of 10x, and turned it into something we can integrate. So that's equal to the integral of a half cos of 20x plus a half dx equals, well, cos integrates to sine, so we get 1 over 2 sine of 20x. But remember, we must divide by the differential of the bracket, i.e. divide by 20. So that makes the bottom 40. Plus 1 half x plus c. So that's how you do questions like that. So let's take another example, and let's put this into an exam question context now. Let's do a few exam questions on this. So this question here is a good one to go through. So it says find the exact value of the integral between pi over 6 and 0 of that. So the first thing I'm going to do here is expand the brackets, which will hopefully make things a little bit easier. So equals the integral between a 6th pi and 0 of, let's just expand it here, make sure we'll miss no terms. So 1 minus sine of 3x, 1 minus sine of 3x equals 1 minus 2 sine of 3x plus sine squared of 3x. So that becomes the integral of 1 minus sine of 3x. 1 minus 2 sine of 3x rather, plus sine squared of 3x dx. Now, there's two parts to this, I think, an easy part and a hard part of this integral. I'm going to divide this question up into two parts. That's part A, and that's part B. So I'm going to do the easy part first. So part A, if I integrate that, it becomes x, and the integral of sine is minus cos, which turns that into a plus 2 cos of 3x. But remember, divide by the differential of the bracket, which is 3, and that's between pi over 6 and 0. So equal to, so sub pi over 6 in, we get pi over 6 plus 2/3 cos of 3 pi over 6 minus 0 plus 2/3 cos of 0. So cos of pi over 2, 3 pi over 6 is pi over 2. Cos of pi over 2 is 0. Obviously that's 0. And that becomes, cos of 0 is 1. So that will become pi over 6 minus 2/3. So that's part A done. So now remembering how we did part B earlier. So it's the integral of sine squared of something. So we're going to expand cos of 2x, the double angle formula for cos of for 2x. And since we're being asked to integrate sine squared x, sine squared of 3x, we're going to write the expansion only involving sine x. But in this one, notice it's 3x that we're integrating. So in this formula, replace x with 3x, which would make that there 6x. So that means now, rearranging that, we get 2 sine squared of 3x equals 1 minus cos of 6x, and sine squared of 3x equals 1/2 minus 1/2 cos of 6x. So now that's transformed our integral into an equivalent form, but that we can now integrate. So that's a half, the integral of a half minus a half cos of 6x dx equals 1/2 x minus 1/12 sine of 6x. The integral of cos of sine we divide by the differential of the bracket. That's between pi over 6 and 0, and let's sub that in. So we get a half of pi over 6 minus a 1/12 sine of 6 pi over 6, and sine of pi is 0, minus a half of 0 minus a 1/12 of sine of 0, again they're both 0, equals pi over 12. So there's our answer to that part, adding our two answers together. Therefore the area is equal to pi over 6 minus 2/3 plus pi over 12, which is equal to pi over 4 minus 2/3. And now we can check our answer on the calculator. So a neat little trick here. Let's go back up to the beginning and actually type that integral into the calculator. So the integral of 1 minus sine of 3x in brackets squared, where 0 is the lower limit and the upper limit is pi over 6. And obviously this is bad practice because it's going to give us a decimal answer. However, that decimal answer can be used to check that answer there. So what I'm going to do is subtract the answer I got from the one the calculator gave me. So take away pi over 4 minus 2/3. If my answer is truly correct, then I should get 0 in the calculator, or a number so close to 0 that the calculator just made a rounding error. And indeed I do get 0, therefore I know that I'm correct. So a neat way of checking your answers. So a final thing that I want to go through now, before we finish, are these results here given the OCR formula booklet, which unfortunately aren't given in the other exam boards formula booklets, just OCR and the OCR MEI course. But these are very useful results that in all of the exam boards you'd be expected to just use. As I say, you're fortunate with the OCR courses that you're given them in the formula booklet, not the case with AQA and EdXL. However, as I say, let's get them learnt, let's use them anyway. So let's apply this first one here. We'll go through this one first, and let's use it to find the integral of tan x an even quicker way than we did before. So the integral of tan x, well again, it's the same as writing the integral of sin x over cos x dx. And what this is saying is when we integrate something, where on the bottom, the differential of what's on the bottom is on the top, then we can just use this result here. We'll prove it in just a second. So here it's almost the case that the differential of the bottom is on the top. The differential of cos x, however, is minus sin x. So I'm going to change the question a little bit, just so that it works. So the differential of what's on the bottom is on the top. However, what I've done is awful, because I've changed the question to suit me. Can't really do that. I want to answer this question here, which is equivalent to that question there, which is not yet equivalent to that question there. I've just put a negative sign in there, but I can adjust for that. I can make it the same as the original question by putting a minus outside the integral. So I've got that there. So minus the integral of that. And now that truly is of this form here, because the differential of what's on the bottom is on the top. So now I can just use that formula. Log modulus of cos x plus c. However, remember, there was that minus there. Let's not forget that. So that makes that a minus log of cos x plus c, which is the equivalent of what we got earlier. So let's prove this first formula now. So the proof of it, well, if I differentiate the right hand side, so let's differentiate log mod f of x plus c. So if we differentiate log, we get 1 over. So it becomes 1 over f of x, but we use the chain rule, times by the differential of what's in the bracket, times by the differential of f of x, which is f dash x, and then the plus c disappears because differentiating a constant gives 0. So that's equal to f dash x over f of x. So we proved it, we're back to where we started. So if we differentiate that, we get that. That's it, proved. Let's have a look at this second one. So let's have a look at the integral of cos to the power of 6x sin x dx. And notice that's the form of this one here, because we've got something wrapped in a bracket, f of x wrapped in a bracket to the power of 6. So actually I can make it even more obvious that this is the case by rewriting this in a different order. If I rewrite this as sin x times cos x to the power of 6 dx, that makes it more obvious. So wrapped in this power of 6 bracket is the cos x, there it is there, so n equals 6. And the differential's at the front almost, because the differential of cos x is minus sin x. So now it looks right if I put that minus sign at the front. So that's just modified the question slightly. It's still the same question, but I present it in a different way to make it so I can use that formula there. So again, for the other exam boards other than OCR, that's a result that you've just got to know how to use. And both these results are integration by substitution, just without doing any of the working. So equals, so now I've got that expression, so it's 1 over n plus 1, so 1 over 7 f of x, which is cos x, to the power of n plus 1, so to the power of 7 plus c. So equals, writing it in a more standard format, cos the power of 7x plus c is that one there. So relatively straightforward question is that. So let's have a look at a few more. Let's do a couple before the end, just a couple of more difficult trig questions. So let's have a look at this one here. That one there. Right, so it's saying, show that that's the case. So with this, the key is knowing your trig identities, spotting that the top of that, so the integral between pi over 4 and 0, spotting that the numerator is actually cos of 2x, and that the denominator, 2 sin x cos x, is sin 2x. So you've just got to know that that there is the equivalent of that, and that there is the equivalent of that. And notice that it's almost but not quite of this form here, one of these ones here. So using that result, which again on OCR you're given what you need to learn for the other exam boards. So the differential of the bottom is 2 cos of 2x. So pi over 4 and 0. So let's write the question out in such a way that it makes it obvious that it's f dash x over f of x. 1 plus sine 2x. But I can't really just change the question like that just by introducing the 2. So I'm going to have to adjust for it by making it a half outside there. So that is the original question, but written in a way that makes it obvious that it's one of these, that we can use that rule there. So equals a half, and that becomes log f of x, so log mod 1 plus sine of 2x between pi over 4 and 0. So equals, let's sub them in, so it becomes a half log of 1 plus sine of 2 pi over 4 minus log of mod 1 plus sine of 0 so that's 0, and log of 1 is also 0, so equals 1/2 log of mod, and sine of 1 plus sine of pi over 2, well, sine of pi over 2 is 1, so that just becomes half log modulus of 2, and the modulus of 2 is just 2, so from that point we're done.